In this tutorial, we'll explore how to compute probabilities in Matlab using a variety of probability distributions that come with the Statistics and Machine Learning Toolbox. We'll begin with the binomial distribution. In all of these examples, we'll be modeling a situation where we're sampling a population with replacement, where our sample size or number of trials is 10 and our probability of obtaining a preferred outcome is 0.43. The first example we see here, we're using the binomial PDF to compute the probability that our sample will contain exactly 7 preferred outcomes. So the order of inputs on the binomial PDF function is the value of our random variable, the number of preferred outcomes, then the sample size, and then the probability of a preferred outcome. The next example computes the probability of containing 7 or fewer preferred outcomes in our sample. And to do this, we use the bino-CDF function rather than the bino-PDF function. The example afterwards computes the probability of capturing more than 3 preferred outcomes in our sample of 10. Finally, our last example computes the probability of obtaining more than 3 preferred outcomes in our sample and no more than 7 out of our sample of 10. If we were actually going to run that fragment of code we just saw, then in the output area where our command line is in Matlab, we would have obtained the following 4 results representing the 4 probabilities that we computed in the order that we computed them. Now we'll look at examples involving the hypergeometric distribution. The hypergeometric PDF and CDF, or HiG, PDF, and CDF functions of Matlab all use similar inputs. They expect the random variable value first, the number of preferred outcomes in the sample, then the total population size, then the special population size, and then finally the size of your sample. And again, this function is used for modeling situations where you're sampling without replacement. In this one particular example, we're computing the probability that a sample of size 10, taken from a population of size 145, that has a special subgroup of size 94, will contain 8 or more members from the preferred subgroup. And so we use the hypergeometric CDF to compute the probability of obtaining 7 or fewer, and then compute the complement of that probability by subtracting that result from 1. When we run this code, Matlab returns an output to us that tells us that the probability of obtaining 8 or more preferred outcomes in our sample just under 25%. Now we'll move on to some examples with the geometric distribution. The geometric distribution in Matlab deals with probabilities of repeating a sequence of independent trials indefinitely until the first preferred outcome occurs. And the random variable associated with this distribution is a count of the number of attempts required before that first preferred outcome occurs. So the geometric PDF and CDF functions both require the same kind of input. You first specify the random variable value, the count of the number of attempts required before that first preferred outcome occurs, and then the probability of obtaining a preferred outcome on any given independent trial. So in these 5 examples in order, we're computing the probability that the first preferred outcome occurs immediately, that no failed attempts were required. The second one computes the probability that 1 failed attempt was required before observing the first preferred outcome. Then we're computing with the CDF, meaning that we are looking at the probability of requiring 5 or fewer failed attempts before obtaining the first preferred outcome. And then we are computing a complement. So we're looking at first GOCDF of 9,0.18, which would compute the probability that 9 or fewer failed attempts were required to obtain the first preferred outcome. But then by computing the complement of that, or subtracting it from 1, we're ultimately computing the probability that it takes 10 or more failed attempts before we see our first preferred outcome. Finally, we're doing an example of a range with an upper and lower bound. So we're computing the probability that 10 or fewer failed attempts were required to obtain the first preferred outcome, and subtracting away from that the probability that 5 or fewer attempts are required in order to see the first preferred outcome. So what this means in short is we are looking at the probability that anywhere from 6 to 10 preferred outcomes or failed outcomes are required before we observe the first preferred outcome. If you were to run these examples in Matlab, you should find that it gives you the following results for each of the 5 examples in the order that we've entered them. In Matlab, the Poisson distribution is handled with the POS-PDF and POS-CDF functions. Both of these require the random variable, or the count of the number of preferred outcomes that are observed within a certain interval, followed by the parameter value lambda, which represents the number of preferred outcomes that one expects to see on average in that same interval. So in this example, we are computing the probability that we would see 100 or more preferred outcomes observed in an interval, in this case a day, when we only expect, on average, there to be 53.33 outcomes during that time period. So we do this by using this POS-CDF function to compute the probability of 100 or fewer preferred outcomes being observed in that interval, and then we compute the complement of that probability by subtracting it from 1 in order to find the probability that there will be more than 100 preferred outcomes during that interval. When we run this code, we find that the probability we're computing is actually quite low, 4 times 10 to the negative 9 or a little bit more. Now we'll move on to some continuous distributions, and we'll begin this exploration with the normal distribution. To compute probabilities with the continuous distributions, we're typically just using the CDF function that is supplied by Matlab. And so I want to compute the probability ultimately that x is lying between a random variable, a normally distributed random variable is lying between 15 and 16, under the assumption that this random variable has a mean of 17.3 and a standard deviation of 2.7. So we can compute the probabilities that x is less than 15 and the probability that x is less than 16 by supplying a vector of random variable values, 15 and 16, into the first position of the inputs of norm CDF. Then we follow that up with the parameter values of the mean is 17.3 and the standard deviation is 2.7. Stored these values in a variable called p, which is going to give us a vector of probabilities for those two ranges. But when we subtract the first entry in that vector from the second, then we're ultimately computing the probability that our random variable falls between 15 and 16. Now, if I want to compute a probability that the random variable falls in some unbounded range, like x greater than 90, then I can just use the CDF function like we would have with any of the discrete distributions. I'll first compute the probability that x is less than 90 using the norm CDF function. This time it appears that I'm using different um, different mean and standard deviation parameter values of 81.35 and 11.64, but 90 is the random variable value. So norm CDF of those three values computes the probability that x is less than 90. But when I compute its complement by subtracting that value from 1, I get the probability that x is greater than 90. An alternate approach to this is to simply use norm CDF as if you were computing the probability that x was less than 90, but supply the optional argument of the string upper at the end of the inputs in this function. And then it will compute the probability that x is greater than 90 rather than less than 90. This works with most of the probability distributions in Matlab. In any case, if I were to run this code in Matlab, we would see the following output appear in our command window. We can see the first result are the two values of p for x falling less than 15 and 16. Then we subtract their difference to find x within that range. And then the last two entries, noticing that they are the same values, those were just our two alternative ways of computing the probability that x was greater than 90. Now we'll look at the chi-squared distribution. Chi-squared distribution requires two entries in general, two inputs. The random variable value followed by the one parameter of nu, or the number of degrees of freedom. So in this example, we're computing the probability that the random variable is greater than 36.41503, given that there are 24 degrees of freedom. And the CDF computes the upper interval, or the probability that x is greater than 36.41503 rather than less than, because we've supplied once more the optional argument of upper. We can see then that this results in a probability of 5%. We'll conclude with some examples using the t-distribution. Now the very first example is not computing a probability at all. And this is just a reminder that with working with probability density functions or continuous probability distributions, we only get probabilities from the CDF functions. The PDF function provides a probability density value, which is just a y-coordinate on the graph of the probability density function. So this first line of code computes a value of the density function associated with the random variable value of 8.2 and a parameter value of 9 degrees of freedom. So to compute an actual probability, for instance, that our random variable x falls between 6.3 and 8.2, given that there are 9 degrees of freedom, we would provide a vector of those two endpoints of our interval to the first input of the tcdf function, follow that with the number of degrees of freedom, or 9. Then, just like we did with the normal distribution, we'll subtract the first value of the resulting vector of probabilities from the second. Notice if you're looking carefully at this code, you'll see that the comments are wrong and misleading. They're referring to a previous example where I was looking at a normal probability that a random variable fell between 15 and 16, rather than this t-distribution random variable falling between the values of 6.3 and 8.2. In any case, if we execute our code for these t-distribution examples, we'll see that the first fragment provided us with a probability density value, not a probability, of 8.8955 times 10 to the negative 6. And then the t probabilities that we finally computed appear in the following two outputs. Specifically, the probability that our random variable fell between 6.3 and 8.2 was really quite small. Specifically, it was a little more than 6 times 10 to the negative 5. Hopefully these examples will help you get started with the different probability distributions that are available in the Statistics and Machine Learning Toolbox of Matlab. There are more than the ones that we've looked at, but you can always go and gain more specific insight on the syntax for using these functions in MATLAB's built-in help and documentation.